This video is part of the Signals and System series of videos. In this particular video, we're going to talk about continuous time, commonly abbreviated to CT, and discrete time signals, which is abbreviated to DT, discrete time. So let's go ahead and first talk about the continuous time signal first. So continuous time, as the name implies, is that the independent variable in this function, or the horizontal axis for this, is time. And time axis in this particular case, you can think of it as being a real number. In other words, you can take all possible values from the range that you are working with. And then the vertical axis would be whatever signal that you are trying to represent, the output signal, the input signal, or some intermediate signal. So that's basically the axis we're going to use. And let's say I'm going to use a blue to just make up a signal. For example, let's say we have a signal that looks like this. This is continuous signal. Why we call it continuous? Because the x-axis is real number, and at every point in time I have exactly one value for this function. So any point on this axis, I can go up here and pick a single point. As you notice, this function is written as a name, whatever variable name you want to give it, and parenthesis t, parenthesis close. This is called continuous time, and most things in the world that we observe, and the way we interact with the world is continuous. There are no gaps from one time to another time. There is another class of signals, which is our discrete time class of signal. And these classes of signal, basically what they are in their essence is we only know the value of these signals at specific points in time. And the way these signals are usually created is we sample our real signals that exist in nature, or the way we in our world, and we just at every given point in time we pick a sample of them. So the way we show this, the x-axis is shown as n. Now remember, n is not time. N is actually a integer number. And so it's an integer number, and it only tells you which sample number you are in. It is integer, which means it's going to go from minus infinity to plus infinity, but it's going to increment by 1. So, for example, if the signal above was sampled at a certain frequency, you may have something that kind of looks like this. Okay. So this would be, let me get a black one so I can give you the axis so you can take a look at what are the axes we draw on this one. So the axis potentially could be here. And this is the way we write this discrete, this is the discrete time function. Notice that we are not using a parenthesis, but we're using a square bracket. And typically on these, we also have a little dot at the end indicating where the end of these signals are. Okay, and then when so in this particular case, this might potentially be -1, +1, 2, 3, 4, and there has to be one at 0 as well. And then -2, -3, and on and on. Now, typically when we sample, these are called samples. So this is the third sample, this is the fourth sample. So if somebody asks you, is this time? The answer is no, this is not time. This just tells me which sample number am I on. For example, if you want the third sample time is here, but you don't know when that is. If you want to know when it is, you need to know when the sampling started and how frequently the samples were taken then you can tell them where you are on the sample. So we are very familiar. I hope you're very familiar, and my expectation is you're familiar with these signals. An example of a continuous time signal might be x of t equals to cosine of 500 pi t. So for every value of t, every possible value of t, which goes from minus infinity to infinity, I have a value, whether you're looking for t equal to 1, or you're looking for t 1.0001 or 1.000234, any value that you have, I can give you an exact value for x of t. Now, when we come down here and we look at this discrete time function, a typical function would be like this. Something like that. Okay, but so I know the value for any n that is integer, but if you say what is the value when n is 1.5, the answer to this is we do not know. Okay, as if you tell me what's n equal to 1, I can tell you what the value is, but n 1.5 is not an integer, which means you're ending up somewhere in here, and we do not have that value in it. And that's a big difference between a discrete time and a continuous time. So now you may ask, why do we bother having continuous time and discrete time? Let me use an example of an audio system to describe when we do. So you've got bands playing and dancing and singing and all that kind of stuff, and then you will have a microphone, and that microphone uses air pressure to translate. And so you've got a mic here. You're going to use the air pressure from all these people dancing and singing and all that kind of stuff to turn this into a voltage. So at this point, you've got a voltage, but what the voltage you have here is going to be continuous. Okay, so that's at this point you've got voltage, but your voltage is in continuous time. Nowadays we have computer systems, and computer systems can store large amount of numbers. So a lot of time we are actually in most of our modern system, except if you're very niche world of folks who want to do analog all the way through, the first thing that happens to this music that comes to the mic is it gets translated from analog to digital. And the digital is actually means that now, instead of having a continuous signal we had over there, we're going to have a discrete set of signals. So which basically means we're going to have a series of numbers. For every time it is sampled, if the voltage is 5, we're going to write a 5 in there. If voltage is 5.6, we're going to write some equivalent to 5.6 in numbers in there. And so at this point, we've got a discrete time signal. We just know the values at the times we are sampling the signal. We do not know what happened between our samples. The reason a lot of people do, a lot of the systems do this to translate everything to digital, the discrete time. Sometimes this is also referred to as digital, simply because we store the numbers in digital, and a lot of time this continuous is referred to as analog as well. Okay, so when it's here, the beauty is that once we got it in number, if I want to have a gain of 2, I'll just take every number and multiply it by 2. If I want to quiet it down, I divide it by 2. We can move the signals around. We can put them closer together, farther apart to change their frequency. So that's very nice. So this is where we process and store data. So this is like on your phone when you have music, all your music is stored in ones and zeros with the numbers, data, digital data. So digital data is here. And then if you ever want to, when you play it back, it puts it into something called digital to analog. So basically for every number that is here, it's going to translate this into voltages. So we're back to continuous time. You come back to voltage. So in here, you basically had discrete value for every given point of time. You have different values. When you get over here, you're back to analog again. Okay, continuous time. And then that you just drive into a speaker, and that speaker basically gives you back air pressure, a variation on air pressure, so you got your sound out here. So sound was an analog signal. You put it in here, the microphone translated it to voltage, was continuous. Then we sampled it with the A to D converter, so it became a bunch of numbers in sequence. We stored it, massaged with it, do whatever we want to do with it. When you want to play it back, we took those numbers, translated them back to the voltage, and we send them to a speaker. And what the speaker does is does a reverse of what the microphone does. It takes voltage and translates it to sound. Now you can hear it and enjoy it again. Okay, so that's pretty much, this is a very good way of thinking about what an analog signal is, what a digital signal is, why people do different things. And this applies to over 90% of devices we have. They take the real world signal, translate it to digital, and then massage it, store it in digital until you need to get it back. Then they translate back to analog and you can use it.